Good evening, Math for Teachers 1. I'm Tyler Draper, and today we're going to go over the 6 math problems that Miss Benzie has assigned us. Go ahead and pull them up here, share my screen with you, get the PowerPoint up, and let's see. Okay, so it's going to be Module 1, Lesson 1, Chapter 1. It's going to be our math problems, thinking critically. So, like I said, I'm Mr. Draper. This is Math for Teachers 1. Okay, so problem 1 says complete the following puzzles. All right, so problem A. We're going to read it together really quick. All right, place the digits 8, 10, 11, 12, and 13 in the circles to make the sum across and vertically equal 31. Is there more than one answer to the puzzle? Show all possible combinations of numbers to prove how many combinations exist which meet the rule of 31. So the first thing we need to realize when they say the rule of 31, so we need to identify all the different equations that equal 31. All right, so we've done that right here on the problem. I've identified that 8 plus 10 plus 13 equals 31. And I've identified that 8 plus 11 plus 12 equals 31. And when we see that those both equal 31. And do you see any other equations that may equal 31? All right. So after we have found that those both equal 31, we have to find out how we're going to align them on the graph. We see that 8 is shared in both equations, right? So where does the 8 go on the graph? If they're both sharing the 8, where would the 8 go? That's right. 8 would go in the middle. See, we'll have our answer here. So we see that 13, very top number, plus 8 plus 10 equals 31. So that checks on the rule of 31. And then 11 plus 8 plus 12, that checks on the rule of 31. And that should be the only combination that we find. All right, problem B, study the diagram to the right. 2 plus 8 equals 10, 5 plus 8 equals 3, 2 plus 5 equals 7, and 3 plus 8 equals 11. So basically what we see in this video, or in this problem here, is that the 2 blue dots equals the amount that's in the very middle. For instance, 2 plus 8 equals 10. We'll do problem 1 first. So we're given a 7 in the top left circle. So 7 plus, we'll identify the top right circle as x equals 15. And then after we do some of our simple algebra, we rearrange the equation and we subtract 7 from 15, and then we should get x equals 8. So the top right circle equals 8. Then we'll move down here. It says, so 20 minus 8 will equal 12. We'll get our bottom right. And we can subtract 12 from 17, and that'll equal 5 for our bottom left circle. Now, this is the most important part, and I see people skip this step often. I skipped one earlier, and I'm almost missing a problem. You have to make sure all the equations fit. Just because you do 3 of them does not mean the 4th is going to add up correctly. So always check. Always do all of our proofs. Don't skip any steps in the process. Okay, so we know that 12 is our bottom left circle. Correct? Okay. Sorry, I was wrong. 5 is our bottom left circle. So therefore, 5 plus our given 7 should equal the middle number, and that's 12. Does 5 plus 7 equal 12? Good, it does. So that means we're correct and that we've successfully done this problem. And we see 7 plus 8 equals 15. 8 plus 12 equals 20, 12 plus 5 equals 17, and 5 plus 7 equals 12. Good job. We've done our first one. Problem 2, we're given the 6, and so we'll solve for the upper left box first. 6 plus x equals 13. We'll do our simple common algebraic equation, and we'll get that the upper left box is 7. Until we have our 7, we'll do our equation, 7 plus x. X will be the bottom left box. Sorry, got a typo there. So we will find that that bottom left box is 4. All right, and then we can do our next problem. If we know that the bottom left circle is 4, and we don't know the bottom right circle, we can identify the bottom right circle as, that's right, we can identify it as x, and we will find that the bottom right circle is 15 when we subtract 19, or 4 from 19. Okay, and remember our final step. So what does 6 plus 15 equal? Correct, 21. We'll add these up real quick just to check. 7 plus 4 equals 11. 4 plus 15 is 19. 15 plus 6 equals 21. And 6 plus 7 equals 13. Good job. Another one done. B3 here. Okay, so we're given the 3 in the bottom right circle. So we see that 3 plus x equals 6. So we're looking for the bottom left circle here. We'll identify that as 3. So 3 plus 3 equals 6. 12 minus 3 equals 9. We get our top left. Then our top right circle. So 15 minus, we already identified top left as 9. So 15 minus 9 would equal 6. So our top right is 6. And 6 plus 3 equals 8. Does 6 plus 3 equal 8? No, 6 plus 3 does not equal 8. So we see that either we made a mistake or this equation is not possible. Let's see. So 3 plus 3 equals 6. 3 plus 9 equals 12. 9 plus 6 equals 15. So yes, we do see that this equation is not possible. Not possible. There it is. We see that with the steps here. Our last problem on part B. Okay, so we're given 8 on the bottom left. 8 plus what equals 18. We find that the bottom right circle will equal 10. Okay, then we'll search for our top right circle. So if we have 10 in our bottom right, 10 plus what equals 16. That's right, 16 minus 10 would equal 6. So we have our top right would be 6. Now, I'm going to challenge you here. I need to know what x equals for the top left. We have two equations that can be set up. We have 6 plus x equals 7 if we wanted to use the top right or the top equation, or we could do 8 plus x equals 9 if we want to use the left equation. So what should x equal? Give you some time to figure it out. That's right, it'll equal 1. So 8 plus 1 equals 9, 1 plus 6 equals 7, 6 plus 10 equals 16, and 10 plus 8 equals 18. And I hope you're starting to grasp the concept here. If not, maybe you can look back over and try them again. Okay, problem 2. 9 square tiles are laid out on a table so they make a solid pattern. Each tile must touch at least one other tile along an entire edge. See the two examples on the right. The squares all have side lengths of 1. All right, so A, sketch all possible figures which can be formed and calculated the perimeters of each figure that can be formed. The perimeter is the distance around the figure. Okay, so the perimeter. When we think of perimeter, we want to think of, I always say, let's think of a pool. So the area is going to be all the water in the pool. The perimeter is going to be the edge upon which we jump in off of. So always think of the perimeter as the outside, right? Okay, let's do 2A real quick. Okay, so it says sketch all possible figures. I've sketched a couple of the figures below here. These ones here. So we see this one is 3 by 3. So we have basically a square. Then we have 1 by 9, which is, just a long line. Then I have some irregular shapes here that we have created. Have some little steps right there. It looks like steps. Okay, and so when we add up the perimeter, let's see. we're going to count up the outside, and each square equals 1. Okay, so let's look here at the cube first. Follow along with my mouse here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the cube, which is all of these squares bunched up as close together as possible. It's a regular shape. There's no irregular shape to it. It's 12. Now, let's look at my mouse again. When we look at, so we can identify that the cube is going to be the smallest possible perimeter that we can get from using 9 cubes. When we look at this irregular shape here, such as the stairs, I've kind of made a little model here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And we see when you look at the 1 here and the 2, we count each face that's showing. It's not, we're not just counting cubes because we're counting the perimeter, the outside. We see that it's 14. So the irregular shapes, they're going to have a little bit more perimeter because there's more sides of the square that are open as compared to in the cube here, where all these on the inside are not counted as perimeter because they're bunched together. Now let's look at the 9 cubes, just a straight line, and we see, you know, I've counted them 1 through all the way to 20. We see that that's going to be the most perimeter because those cubes are open and going to be able to count almost each cube. We're using it for the perimeter, whereas in this one, we're not counting the perimeter for this cube in the 3 by 3, and we're not even, this one doesn't get any perimeter for the stairs. So we can tell that in this one, all the cubes are being used for perimeter. So as we make a 9 by 1, so 9 square cubes just stacked on top of each other, that's going to be the maximum amount of perimeter for this equation. I hope you understood that. Hope you can see the patterns and how when we realign the cubes, it's going to change their perimeter. However, it will not change the area. We know the area, that's not going to change, but the perimeter can change when we move the cubes. Just like if we were to add a little jacuzzi to your pool, we're going to add perimeter to the side of the pool. Okay, so we answered B. We said which figure has the least perimeter and which has the greatest. So the cube, where it's compact and tight, is going to have the least perimeter. The greatest is going to be a straight line of cubes because we have all this perimeter on the outside. That's going to be counted. That was 2. Okay, number 3 here. The triangular numbers and the square numbers are shown below. So as we can see, we go from 1 to 3 to 6 to 10. We're given this equation. We see 1, 4, 9, 16. Consider a new sequence of dot patterns below and complete parts A through C. Okay, so let's take a look at well, what's a 5-sided shape? That's right, the pentagon. When I think of pentagons, I always think of, well, the Pentagon that, you know, is a part of the U.S. government. 5 sides, remember, 5 sides. So first, from my mouse, we go from 1, then we have 5, and we just keep adding an extra layer each time. So draw the next 2 figures to continue the sequence. Okay, so let's see. The first shape here is 1. The next has 5 dots. Next has 12. Next has 22. And then this is a handmade model that I've created. This one will have 35. You see, we add this extra layer where my mouse is tracing. And then we add more and go to 51. Okay, it says list the sequence of numbers that corresponds to the sequence of part A. These are called pentagon numbers, so we can tell we go from 1, 5, 12, 22, 35, 51. Okay, now part C and D. We'll do these real quick. So C, add 4 more equations to this list on the right. The equations are suggested by parts. Let me move this. So we are given that 1 equals 1, 1 plus 4 equals 5, 1 plus 4 plus 7 equals 12, 1 plus 4 plus 7 plus 10 equals 22. So did you notice any patterns there while we were looking at that? So we go from 1 to 1 plus 4. So we see that we went up 3. 4 minus 1 is 3. And then this next set here, we went from 1 plus 4 plus 7. So we added 3 again. 1 plus 4 plus 7 plus 10. We went from 10 minus 7 is 3. 7 minus 4 is 3. And 4 minus 1 is 3. So each time we're going up by an increment of 3. So let's take a look here. These are the 4 that we are given, and we're going to add 2 more. So 10 plus 3 equals, that's right, it equals 13. Then, of course, we add all of our totals together. We get 35. And then after we have 13, 13 plus 3 equals 16, correct? And that equals 51. That was pretty simple. Just a pattern. We see that we're adding 3 each time to our last number. Okay, so D. Observe that each pentagonal number is the sum of our arithmetic progression. Compare the 10th term. That's Hope. She's in our Math for Teachers 1 class, so we're both communicating back and forth. I hope she watches this videos and laughs about that. Okay, so it says compute the 10th term in the arithmetic progression 1, 4, 7, 10. What is the question was, what is the 10th term? So what I did was I just made a graph with all of our numbers. Oh, she just messaged and said that message was for Miss Benzie, not for me. So that's going to be funny. I hope she watches this. Okay, so first, here's the 4 that we were given, all the way to 22. Here's 51, which we just made over here. And then each time we're adding 3. So 16 plus 3 equals 19. What does 19 plus 3 equal? That's right. It's going to equal 22. Then so we'll have 22 here, 22 there, 22 plus 3 will be 25. So then we have 22, 25, 28, all the way down here. So 1 plus 4 plus 7 plus 10 plus 13 plus 16 plus 19 plus 22 plus 25 plus 28. Goodness, that's a lot. Equals 145. So that is our 10th term. As we can see here, we go all the way down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Our 10th term equals A, 145. Good job. Okay, now E. E says, show the formula for pentagonal numbers and calculate the 9th, 10th, and nth term. So what we need to do here, we need to create the formula. So let's use the first term for example. So x equals 1. Our first number is 1. So 3 times 1 equals 3. Well, let's see here. We know that 3 times 1 equals 3. But we're looking for x, which should mean that 3 times 1 equals 3 should equal, and we know that 3 does not equal 1. So we're going to have to subtract from that coefficient, from our variable that we've created. So let's see. So 3 times 1 minus 1 equals 2. That does not equal 1. That would equal 2. So 3 does not equal 2. 3 times 1 minus 2 equals 1. Okay, so let's try this formula for the second and third term. So 3x minus 2, or 3n minus 2. N would be our variable. So our 9th term was supposed to equal, let's see, our ninth term. So let's try this formula. 3 times 2 minus 2 equals 4. 3 times 3 minus 2 equals 7. Let's see, so our third, so we multiply it times, here we go, we got our third number here, third term, and that equals 7. 3 times 2, so 3 times 2 minus 2, so our second term should equal 4. There it is, that equals that. And then 3 times 3 minus 2 should equal 7 for our third term. So our third term should equal 7. All right, looks like we got it. Our ninth term, let's go down to the 9 here, should equal, we decided that was what, 25. So 3 times 9 minus 2 equals 25. 3 times, our 10th term should equal 28. And it does, all right. So actually, we see that our 10th term actually equals C, 28, not 145. I misspoke. So our nth term would equal 3n minus 2 equals the nth term. Solved our equation. Good job. Okay, problem number 4. The figure to the right shows an addition pyramid in which each number is the sum of the two numbers immediately below. For each of the incomplete addition pyramids, show what the values in each square can be determined by forming and solving an equation in the unknown variable shown. Write an equation to solve each pyramid. Show each step used to solve each equation. Okay, so we have these 4 problems and their pyramid equations. Each of these 2 squares, so let me grab my mouse here. So for instance, 7 plus 3 would go here. That would equal 10. Or as we see here, so 3 plus 5 equals 8, 5 plus 9 equals, or 5 plus 4 equals 9, 8 plus 9 equals 17. So we're able to see that example. Okay, so A. Okay, we see that x, 7, and 3. So first thing, the 2 bottom boxes equal the amount above it. Using variables and equations, we can solve this, okay? So this box here, where my mouse is, what is that box going to equal? Well, we know that box is going to equal x plus 7. We may not know what the variable x equals just at this moment, but let's just fill our boxes first, and then we'll get to it. And of course, 7 plus 3 equals 10. See, for example, I have that here. 7 plus 3 equals 10. So we got 10. All right, so we'll move here to A. X plus 7 there, 7 plus 3. So here it is. We have 7 plus 3 equals 10. We got our green 10 here. And we know this row here is going to be our x plus 7 that we have up there, plus 10, and it's going to equal 25 because remember our 2 boxes equal the exact number above it. So equals 25. Simple algebra, we'll get, let's see, 7 plus 10, 17. So x plus 17 equals 25. 25 minus 17, we get 8. So x equals 8. 8 plus 7, remember that was our equation there, equals 15. And just to check, 15 plus 10 equals 25. So we've completed our first pyramid. All right, so let's see for B here. All right, so first let's get our formulas boxed in here. And for this one, I've labeled these with terms. So this box will be Z, this box will be L. So take a second just to make sure we're understanding the concepts. Determine what goes in the boxes of each one. All right, so as we can see here where my mouse is, 1 plus Y equals Z. Y plus 2 equals L. That's how we know that they go in those boxes. Because remember, each box equals, it's 2 bottom boxes equals the amount that's above it. Okay, so we'll solve this. So if we know that 1Y, 1 plus Y, and Y plus 2 that it's going to equal 15 because we have filled in these equations here on B. Look over here at this one, and we got it all wrote out here. So then after we do our property, we see that 1 plus 2 equals 3, y plus y equals 2y equals 15. So then we have 2y equals 12, and y will equal 6. And then we're able to plug and chug the 6 for the y in both of the equations. And we see that it'll be 1, y equals 6, and of course our 2 that was given, and then y plus 1, so 6 plus 1 equals 7, y plus 2, so 6 plus 2 equals 8. We have our numbers. Good job. Problem C. All right, so first we need to identify the bottom middle number. So we'll call that bottom middle number Q. So we're given this number here. So we're given the 2 and the z. So this middle number is going to equal 2 or z minus 2, because 2 plus that number equals z. We can turn that around and use the subtraction because they're both related. Remember, subtraction and addition are related. We can always flip the properties to determine it. So we see that z minus 2 equals the middle box. Okay, and right here, if we know that z minus 2 is going to equal that one, then we can use z minus 2 plus 9 to find the box that's right above it. Because remember, we said the two bottom boxes equal the amount that's above it. So we'll figure that out here. It says, now that we have the bottom middle number, which is z minus 2, we can figure out the top right. We see that z minus 2 plus 9 equals z plus 7. So z plus, we're going to work the middle layer first, right here. So we see z plus 7 equals 27. Simple algebra gets us to where z equals 10. So we see that if z equals 10, we found our z. Z plus 7 will equal 17. Then z minus 2 equals 8. And let's just check just to be sure. 2 plus 8 equals 10, correct. 8 plus 9 equals 17. 17 plus 10 equals 27. And we have done another problem. Good job. All right, and that was all those for number 4. Now, number 5. Let's see here. Okay, so 4 married couples belong to a bridge club. The wives' names are Kitty, Sarah, Josie, and Ann. Their husbands' names, in some order, are David, Will, Gus, and Floyd. Use the table below to sort out who is married to whom. Okay. So I made a similar table to this to determine, and this is just simple process by elimination and using the information given to make it easier for us. And we know as we go along, and if we know someone's married to one person, you can only be married to one person usually, so we can mark the rest of them out. Okay, so let's take a look here. Okay, so Floyd is Josie's brother. Okay, so Floyd is Josie's brother. Well, we can assume that Floyd is not, and Josie, brothers and sisters, are not going to marry each other. So we'll go out on a limb there. I know sometimes that happens, but we're gonna imply that that's not going to happen this time. Okay, so follow my mouse here. We have Floyd and Josie. I put an X. X means they're not married because I said they're brother and sister. Now Josie and Gus dated some, but then Gus met his present wife. Well, if they dated and they're not married, we know of course we know they're not married, but we do know they dated. So Josie and Gus, so let's follow Gus all the way to Josie. I said X, they dated some and not married, so that's another X. Kitty is married to Will. Okay, so that's a big one. If we know that Kitty is married to Will here, I put a yes. We know that she's not married to David, Floyd, or Gus. So that's just a big help because that's going to take many names off the list. Okay, and if Kitty is married to Gus, well, or Kitty is married to Will, we know that none of the other women are married to Will as well. So he's married to Kitty, married to Kitty, married to Kitty. So all these are X's, and all three of these are X's because we know that they're married. So that takes a lot of names off the board. Okay, so Anne has 2 brothers. Now, that is a good key. We'll come back to that. Anne's husband is an only child. Okay, so Anne's husband is an only child. Well, Floyd is Josie's brother. So we know Floyd is not an only child, correct? If Floyd and Josie are related, they're not only childs. So let's see, we'll go down to Floyd here. Okay, let's see. Anne has 2 brothers, and okay, so we know that they're married. Okay, so Josie dated some not married, ex-brother and sister, and Will is married to Kitty. So we know that David and Josie have to be married because she wouldn't marry her brother. Josie wouldn't marry her brother Floyd. Will's married to Kitty. Josie can't be married to 2 people. And we know that Josie and Gus dated, but they never got married. So we know that by that process of elimination here that I have marked, David is married to Josie. So we have that cleared off, and we can clear David's name off. Okay, now Anne has 2 brothers. Anne, okay. Well, let's see. We know that Floyd has a sibling, so we can mark off Floyd for right here for them. And well, Will, we already know Will's married to Kitty. And so that's our only option. And David is married to Josie. We already came up with that solution. We know that Floyd and Anne have to be married because that's our only option. If Gus is the only one without a sibling, and that's all the information we're given. We're going strictly off information given. Okay, and then if that's the case, and all 3 of the other people are married, then our only option, we know that it says that Kitty is married to Will. We determined that Josie had to be married to David after we marked out all her 3 other options. And then, so Floyd has to be married to Sarah because those are our only options left. So in this process, we're going to make a table, and you're just clearing them out one step at a time, as I just did. And that was problem 5. Good job. Okay, problem 6. Consider the trapezoidal numbers 1 plus 1, 1 plus 2 plus 2 plus 2 plus 1, 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 1. The nth trapezoidal number is 1 plus 2 plus n plus 2 plus 1, where n is a positive integer. Okay, so create a dot pattern representation of the trapezoidal numbers. So we'll go to 6A here, create a dot pattern. Follow my mouse here. We see 1 plus 1 plus 1, comma. Our next one's 1 plus 2 plus 2 plus 2 plus 1, comma. Our next one is 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 1. And then our next one, we would go a step beyond that and have 4 in the middle as well. It's just a pattern. I hope we see that. So that was A. Oh, B. Okay, we'll read this together. Notice that 1 plus 1 plus 1 equals 1 times 3. So each side of that equals 3. 1 plus 2 plus 2 plus 2 plus 1 equals 2 times 4. So each side of that's 8. And 1 plus 2 plus 3 plus 3 plus 3 plus 2 plus 1 equals 3 times 5. So each of that equals 15. Show how the dots in a representation of a trapezoidal number can be rearranged into a rectangle with 2 more columns than rows. Okay, so these down here where my mouse is, follow along here. This is what we just determined on our other problem, what our dot representation would look like. And as we can tell, if we create 2 more columns than rows, we can make complete squares. So let's look at this one. We have 1 plus 2 plus 2 plus 2 plus 1. Here, we're just going to pick up this dot and bring it right here, creating this 2 by 4 to fill in that last column to make a complete square. And same for this one. We pick this one up, move it here, and we pick up this dot, move it there, making complete squares. So what we're doing is we're making 2 more columns than rows. So we're making less rows but making more columns. So instead of it being slanted like my hands are here, we're just going to pick that dot up, move it to the top. We're going to make a better, more compact rectangle to fit in there better. And that's what this concept is talking about. Okay, 6C, using inductive reasoning, show what general formula gives the nth trapezoidal number. Nth trapezoidal number equals n plus 2 in the row, so 1, 2, 3, and 4. Okay, so basically what we're doing here, we're seeing the nth number. So we have 1, we have 2, 3, 4, and that's how we're going to add up how many dots are in the trapezoid. So we see 1 times 1 plus 2 equals 3 times 1 equals 3. So we see 1 row, and we get 3 dots. 2 rows, so 2. So we do our parentheses first. So 2 times 2, 4, but times 2 is 8. We have 8 dots. 15, 24. So n times n plus 2 is our trapezoidal formula. And that's all, folks. Thank y'all so much. And I hope y'all were able to learn from my lesson. And I appreciate y'all for tuning in. And thank you so much. Have a wonderful day.